Hello again, everybody. Welcome to Lecture 10 of Environmental Sciences 347 Climatology. We're going to delve briefly into two topics during this lecture. The first is the instrument-based climate record, which is basically thermometers taking us back to the end of the 19th century, and a quick look, a real overview of the climatology of severe weather. And severe weather is kind of a catch-all term for thunderstorms, tornadoes, hurricanes, the kind of weather that does damage. Sometimes you hear it called extreme weather, but severe weather is kind of the catch-all term that you'll hear used in meteorology a lot. So first up, what does the instrument record tell us? Well, when we go back about 150 years and look at the global climate patterns, specifically with regard to temperature patterns. We know the equator is where most of the sun is focused during the majority of the year. I mean, there's always this little fluctuation, how high the sun is in the sky during the time of year because of the Earth's tilt. The heat equator, if you will, is this latitude of the highest average annual surface temperature. And because it's actually a little bit warmer in the northern hemisphere than the southern hemisphere, this heat equator is actually about 10 degrees north of the true geographical equator. This is the place where the mean isotherms, and remember, isotherms are lines of constant temperature, are symmetrical with respect to the heat equator, decreasing in magnitude toward both poles. So each year, as the year progresses, the isotherms in both hemispheres follow the sun, shifting north and south in tandem. What does that kind of mean? Well, I'll show you graphically in just a minute. But first, why is the northern hemisphere warmer overall? Three key reasons. First of all, Antarctica is just insanely cold, way colder than the North Pole. Massive ice sheets in Antarctica keep the mean temperature of the southern hemisphere lower. We do have ice sheets in Greenland, but they are smaller than Antarctica. The North Polar region is ocean. So an ocean is going to store more heat energy. The North Pole is over top of the Arctic Ocean. The South Pole is a big honking continent with ice all over it. So the North Polar region, being oceanic, is going to be milder. In turn, there is more land away from the immediate polar regions in the northern hemisphere. So that's going to absorb more incoming solar than the water majority southern hemisphere. Remembering that water is kind of a moderator in temperature. All right, so that when the sun does get high in the sky in the southern hemispheric summer, a lot of that energy is going into warming up the ocean, which takes a lot more energy than warming up the land. Since we have more land in the northern hemisphere, overall the northern hemisphere is going to be warmer. So those three things combine to make the northern hemisphere a little bit warmer overall. So two graphics here to kind of illustrate that. First is the average temperature for January, and this is in degrees Celsius. So think about northern hemispheric winter, southern hemispheric summer. And the thing I want you to really notice in that top one, and these are lines of constant temperature, average temperature for January. All right, they're very, very tightly packed north of about 30 to 35 degrees north latitude. Have a very strong contrast in temperature from the tropics to the mid-latitudes and into the polar regions. If you contrast that in the bottom graph to southern hemispheric winter, that's July. So again, our summer's their winter. You don't see as much of a rapid change or a closely packing of those isotherms in the southern hemisphere, with a couple of exceptions around the Andes and the Pacific coast of South America, and to some extent along the Indian Ocean coast in Africa and the northwestern coast of Australia. But it's a lot more pronounced in the northern hemisphere because you have land masses that extend from near the pole continuously all the way to the tropics. That is not very common in the southern hemisphere. As you travel away from Antarctica, you run into the Southern Ocean, Indian Ocean, Atlantic Pacific before you start reaching continents again, whether that be Africa or South America. All right, so there is more ocean. There's more of a moderating influence in the temperature in the southern hemisphere versus the northern hemisphere. And that whole thermal equator, if you will, or that area where the temperature is the warmest, tends to be, again, a little bit north of the true equator, the true geographical equator, because of this effect. Now, precipitation patterns are going to be different. These go back to things we talked about earlier in the course, Hadley circulation. We talked about the trade winds. We look at ocean currents. We look at big areas of semi-permanent high and low pressure. These things all contributing to global precipitation patterns. We mentioned earlier these areas near about 30-ish degrees north and south latitude tend to be areas that are a little drier because they're the sinking component of the Hadley cell is there. Whereas you have the rising component of the Hadley cell near the equator, the sinking or warming part of that cell is near 30 degrees north and south latitude. So you tend, all else being equal, to have slightly drier conditions there. Having said that, because we still have ocean currents, you see exceptions to that. When you look between about 20, 30 degrees south latitude in South America, you see about 20, 25 degrees south latitude over Africa. All right. And of course, where we are in the southeastern coast of North America, it's fairly damp, if you will. And Florida is certainly not dry, except in the wintertime. But you see these broad areas. You can pick out the Sahara Desert pretty easily there in North Africa. And a lot of interior Asia is quite dry. Although Southeast Asia, South Asia is a lot wetter. And that ties back into the monsoon circulation in India, Pakistan, which also ties back into the very cold, dry Himalayas to their north. All right, so the precipitation patterns are governed by all those things. So in the tropics and subtropics, this area that's, 20, 30 degrees north and south latitude, seasonal shifts in the intertropical convergence zone, remember that kind of goes north, it fluctuates north and south across the equator through the course of the year. All right, these are going to be responsible for the rainy season and dry season climates. Now, in our part of North America, we don't really have a rainy season or a dry season. All right, we're reasonably and favorably damp most of the time. Not like Oregon and Washington, which are wet a lot more frequently, or certainly Southeast Asia, the Amazon, Sub-Saharan Africa, the Sahel. Those places get rain a lot of the time. But think about a couple of places that have legit dry and wet seasons. One place I think of closest to us is Florida. Florida is actually drier, much drier in the winter than they are in the summer. Summertime, you hear the stories, they get a thunderstorm every day. All right, that does not happen in the winter. Now, it does not say it doesn't rain at all in the winter, because it does. But December, January, February tend to be the relatively drier seasons in Florida, especially South Florida. All right. Conversely, it's very wet in the summer because it is so hot. And we'll talk about why there's thunderstorms down there almost every day a little bit later in the lecture today. But the monsoons, another issue. They're India, Southeast Asia, or really Central Asia, so South Central Asia, back to the Himalayas. Massive shifts in pressure during the course of the year. All right, from very cold, high pressure over the Himalayas, racing outward off the continent, pushing dry air off of the continent into the Indian Ocean. That keeps precipitation from forming farther inland. The opposite effect happens during the summer. The interior continent gets very hot. You have a broad area of low pressure, and that surges moisture inland into India, Pakistan, from the Indian Ocean, goes up the slopes of the very, very tall Himalayas and puts down a tremendous amount of rainfall. And that's the monsoon circulation. Remembering monsoon, that term gets tossed around a lot, thinking it just means a lot of heavy rain. It's not a monsoon. The meteorological, climatological definition of a monsoon is a large seasonal shift in wind circulation. There's a small monsoon circulation in the southwestern United States. Not that it is wet at all in July and August in, say, Arizona or New Mexico, but they do have the tendency to have a few more thunderstorms here or there in their monsoon circulation because you do have a little more flow coming off the Gulf of California in that part of North America during those times of the year versus the winter and early summer. I mean, the hottest time of year in Arizona is actually May and early June. It's not July and August because of that monsoon circulation tends to bring in more cloud cover and at least the opportunity to get some rainfall. Not surprisingly, rainfall is most reliable in the maritime climates, those that tend to be closer to oceans and seas, and much less reliable in interior locations, continental climates, arid regions. I mean, look, it does rain in Minnesota and central Canada, but it is not a reliable rainfall. It's not a rain that you can kind of count on through the course of the year. Those areas are much more susceptible to droughts because the rainfall is just not as reliable. Part of the reason for that, these are these big areas of high pressure, these ocean gyres, which are driving ocean currents. We talked about these a few lectures ago. Just think about the Atlantic there, the North Atlantic. There's that broad gyre of high pressure, which drives the ocean circulation from south to north in the coastal southeast and east coast. That's why it helps where it tends to be a little more humid here. And that's why it's a little bit drier on the other side of the ocean basin there, on the eastern side of the Atlantic, toward the Mediterranean. Let's say, North Africa, Portugal, Spain, Morocco, they do not get as much precipitation. Why? Because they've got a cooler ocean current coming down from the north that helps to stabilize their atmosphere and inhibit, maybe not prevent, but inhibit a lot of storm formation. And we see that similarly in other locations, like the southwest coast of Africa, the southwest coast of Australia. Because remember there, an ocean current coming from the south is coming from Antarctica, so that's cold. So these play a large role in determining how much precipitation you're going to get through the course of the year. Trying to calibrate or figure out how much the temperature has changed globally over the past 150 years by looking at the instruments is still a challenge in and of itself. I mean, the instrument-based global average surface temperature records are still essential for trying to understand climate variability and any kind of and trying to identify any kind of longer term climate change, longer term trends. So when you examine a comparison of different temperature records and look at them together, you get a better idea of what's going on. And what I mean is that there's no one perfect way to figure out what's the global average temperature because we don't have thermometers everywhere. We don't have ocean buoys everywhere. You have to make some assumptions. You have to make a few relatively good guesses about where to parameterize or where to make an assumption about this or that. And there's no one perfect way to do this. So different organizations, labs, if you will, make slightly different assumptions. And then we look at them all at the same time. We say, well, you guys came up with this. You folks came up with this. You gals came up with this. You did it this way. You did it this way. You did it this way. Well, what was the answer? And you can see from the graph there, there's three different organizations doing that. Hadley CRUT 3, which is the Hadley Climate Research Unit in the UK, NCDC, which is now NCEI, or basically NOAA, the U.S. National Oceanic and Atmospheric Administration, and then GISS, GISS, which is NASA Goddard Institute for Space Studies. So each one of these organizations is doing the calculation on their own, making their own set of assumptions. And even though there's a little fluctuation in each one of those graphics, they all kind of sing the same tune. The notes are a little different, but the tune is about the same. And then about 10 to 15 years ago, another organization, basically University of Cal Berkeley, decided they wanted to do it too. So they incorporated another whole set of assumptions and said, you know what? NASA does it, NOAA does it, Hadley does it. We want to do it on our own. Not that they don't trust the other ones, but they want to do it their way because they think they found a better way. And what they found out is we plot theirs up there and it really matches the other three. So that's 4 different labs doing the calculation 4 different ways and still getting the same basic idea, is that the temperature is more than a degree Celsius warmer now on average than it was back in the 1960s and early 70s. And then you go back to, let's call it early industrial times, the late 1800s, temperature's gone up 1.5 degrees Celsius, which is pushing 3 degrees Fahrenheit, which is quite substantial. Remembering that during the last ice age, the average temperature was about 10 to 12 degrees Fahrenheit cooler than now. And again, climate doesn't change like that movie Day After Tomorrow. You don't wake up in a week and a half and everything is flooded. It does take time, but geological time, not human time. Do remember that there is a lot of area that we cannot stick thermometers in. Think about the oceans and the seas. We've done a very good job the last 10 or 15 years doing remote sensing, installing buoys and floaters, these things called Argo floats. Those have all come online recently, but we've had to do a lot of calibration. I say we, I mean the scientific community, have had to do a lot of recalibration to old sea surface temperature measurements. I mean, back in World War II, you took a bucket and you threw it overboard, plopped your thermometer in the water, and that was your sea surface temperature. Now we have much more accurate ways to do that in terms of intake and electrostatic thermometers, okay? But those things have to be calibrated from past measurements. What we've generally seen was the temperature nudging upward from the end of the 19th century till about World War II, and then downward after World War II, because effectively there was a big boom in the economy, the post-war boom. And there wasn't a lot of environmental protections back then, so we put, as a global society, a lot of crap up into the atmosphere. Sulfate particles and the like, reflecting a lot of solar energy. So the temperature held or dropped a little bit. Then Clean Air Act was established in 1970. Greenhouse gases started to increase. Those two things started seeing the temperature back up. Now, don't think for a second that all the global warming is because we clean the air. I mean, for one thing, clean air is a good thing. All we were doing in the mid part of the 20th century was masking a planetary warming signal and making the air worse to breathe. All right. So I'd rather have the clean air, and we could still deal with the warming environment. Remember, again, when we look at the global average temperature, we want to look at land and ocean together. All right, so when we look at the longer term here from 1880 to the early 21st century, the top one there is land and ocean together. The middle one is just the ocean. The bottom one is just land. And if you look at all three of these, you see that the A and B are much more closely linked than, say, A and C. You know, the land is much more variable than the ocean. And that makes sense. We know that it takes more energy to raise the temperature or lower the temperature of water. So the temperature of the water, 70% of the planet's surface, is what's really driving the larger term or the longer term global average temperature. All right. The land is important, but when we look at the entire driver, that's going to be dominated. That part of the equation, land and ocean, is going to be dominated by the ocean. And the oceans, by and large, have warmed up about a degree or two Celsius since the end of the 19th century as well. So, overall, the magnitude of the overall temperature change in the 20th century, while it is up, it does vary among regions of the globe and the United States. All right, so the temperature record for the globe is not in the same direction at the same rate everywhere because of what we've seen before. Some places are going to have wetter summers, wetter winters, so their temperature patterns will change at a different rate. Their precipitation patterns may change. Not everybody warms at exactly the same rate in a global warming situation. They just don't. There are other things to consider. How weather systems move, how much precipitation you get, how much your precipitation what your normal, if you will, precipitation average. These things go into the larger picture when we look at the planetary warming signal, which is why it's called climate change, because not everybody on the globe warms at the same rate. I mean, we know the Arctic is warming 2 to 3 times faster than the middle latitudes. That's why we say climate change. The climate is changing in different ways in different parts of the globe, even though the globe overall is warming. And don't fret too much about all these little charts here, but the point being is not everybody is warming at the same rate. Whether you're looking at the continental U.S., just the western U.S., the northeast, north central states, east, north central, whatever. Everybody's warming a little bit different, but just about everybody is warming. Some places warming faster than others. One trend that we do see is that colder climates do tend to warm faster than colder climates. Right? Climates that tend cooler and drier are tending to warm faster than ones that have started off relatively warmer and more moist or wet or rainy. Again, that makes intuitive sense when we think about it. If it takes more energy to raise the temperature of water, if you're in a wet climate, it's going to be harder to raise the temperature. Same thing if you're cold versus warm. If something is 10 degrees versus 15 degrees, you add the same amount of energy to both, you're going to get a bigger jump in the temperature on that thing that's 10 degrees versus the thing that's already 15 degrees. Though both warm, but the thing that's colder is going to reflect a bigger change in its temperature than the thing that's already relatively warmer. And that's a lot of what we see in the southeast during the summer. Southeast United States, in the summer, it has not gotten that much hotter because it's such a hot and humid climate to start off with. Conversely, places like North Dakota, Minnesota, in the dead of winter have warmed up tremendously in the past 50 or 60 years because they're so cold and dry to start off with. Revisiting what I mentioned before in terms of trying to calibrate the data, there is a lot of hemming and hawing and gnashing of teeth about the integrity of the instrumental data, all right, looking for potential sources of error because we do have the gaps in the monitoring networks over the oceans. We have seen instrumentation technology advance in the past 40 or 50 years, all right, and yes, there has been urbanization. Some places, we've heard the urban heat island, where it is warmer in an urban environment than a rural environment. All these things have to be taken into consideration, and they have been taken into consideration. I've got a good friend who works at the National Centers of Environmental Information who deals with these things every single day at their office in Asheville, North Carolina, trying to be sure that they've calibrated the data correctly. In fact, when they take the data raw and don't calibrate it, it actually shows a warmer signal than what we than what we've accepted to be true. When we calibrate the data, the warming signal is not as strong. So it's not like the data is being cooked to make it be warmer, to make it show warmer. If anything, the processing of the data has edged back on the warming signal. So if anything, there's a cool bias introduced in calibrating the data that's available. So, in summary, the Earth's climate has warmed over the past century, and warming has accelerated, especially since the 1970s and 80s. And right now, the only plausible explanation, we've looked at sunspots, we've looked at cosmic rays, okay, the latter part of the 20th century and now into the 21st, there's been a steady buildup of carbon dioxide and other greenhouse gases, also known as infrared active, infrared absorbing gases in the atmosphere because of the combustion of fossil fuels. You set carbon on fire in an atmosphere that has oxygen, you get carbon and oxygen, CO2, and that's an infrared active gas, or enhancing the natural greenhouse effect. Remember, without the greenhouse effect, the whole planet would be 60 degrees colder than it is now. It'd be a big ice ball. All right, and we wouldn't be here probably. All right, so a little is good, but what we're worried about is too much of a good thing. So, climate variability and change are not the same everywhere in direction or magnitude. And we also have to be mindful of singularities or very high impact weather events, weather episodes that occur about a certain time of year that are beginning to happen more frequently than chance would dictate. In other words, whatever kind of big bad weather event, bad hurricane, bad windstorm, bad snowstorm, whatever, bad flood, you think, wow, this is the once in a 100-year flood, which doesn't mean it really happens once every 100 years. It means statistically it happens about once every 100 years, or there's a 1% chance of it happening in any year. But because the climate has warmed, we've enhanced the water cycle, the hydrological cycle. That cycle of evaporation, condensation, and precipitation gets ramped up. You get heavier precipitation, more evaporation. All right? These kinds of events that might have happened once every 100 years start happening once every 20 or 30 years. Or the event that happened once every 20 or 30 years happens every 6 or 7 years. So the frequency of these extreme events begins to happen more regularly. Not every year. It's not a new normal. You have a bad weather day. It's going to be like this all the time. No. But something that might have only happened once every 50, 60 years starts to happen once every 20 or 30. And when we talk about the increasing frequency of extreme events, that's what we're talking about. So when we examine how we handle this numerically, mathematically, the global climate models, and if you haven't, please go back and watch that TED Talk with my friend Gavin at NASA talking about climate models, because they're good. They're not perfect. They're tools and they're good. They have skill, S-K-I-L-L, skill. That's the important word to remember here. They predict or project the continuation of the current warming trend will be accompanied by an overall increase in precipitation. All right? But exactly how that's going to be distributed across the globe is still a little bit of a question. The short version is that wet places are expected to get wetter, dry places are expected to get drier. That's the broad idea. Climates that are already arid or dry are expected to continue to be that way or get drier. Places that are already wet are probably going to get wetter, which means flooding. And that brings us to severe weather and high impact weather, extreme events, all these things under that umbrella. High impact weather, weather that breaks stuff and hurts people, severe weather, right? So there are lots of different types. But we want to start off with the most basic type, which is just thunderstorms. And not every thunderstorm is damaging, right? And thunderstorms come in different different scales, different intensities, different maturities, all right? But basically, you've got some kind of warm, humid air racing up into the atmosphere very quickly, condensing, forming a big kind of cauliflower type cloud. It goes up high enough, and you start to get ice crystals forming in that cloud, and you begin to separate charges in the cloud. So you get electrification, thusly lightning, and then thunder. All right. And then in time, it rains itself out and dissipates. The short or single cell, if you will, thunderstorm, what you see there is that idea. You've got just a chunk of hot air rising up very rapidly, condensing, raining itself out over the course of maybe 20 or 30 minutes. Those are most common in our part of the country or our part of the world in the mid to late summer, let's say late July and August, when there's not a lot of temperature contrast out there. It's just hot. Those are the single cells. Sometimes you can get these things clustered together, multicellular or full on a line of a cluster, a multi-cell line cluster, if you will, or supercells. Supercells are the Mac Daddy of them all, if you will. Those are the thunderstorms that will ultimately produce tornadoes, right? The big tornadoes, like you see them on TV kind of tornadoes, all right? The ones that we tend to associate with the ones in the plains, Texas, Oklahoma, Kansas. Those most, if you will, photogenic type storms. A couple of other classifications of thunderstorms, and here in the Middle Atlantic, Southeast, squall line is most common. It's an elongated cluster of thunderstorms that's accompanied by a big gust at the leading edge of it. It's called a gust front. If you think about, it gets dark right before a thunderstorm, and sometimes before the rain hits, it gets breezy and it gets a tiny bit cooler. All right, before the rain gets there. All right, what that is rain-cooled air that has run out ahead of the main thunderstorm. In other words, you've got this thunderstorm here, and it's raining like crazy. That rain-cooled air rushes out ahead of the thunderstorm. And that boundary between the rain-cooled air and the hot, humid air is called a gust front. All right, and that because the winds get really gusty once you get on the other side of that. The temperature will drop 10 or 15 degrees before the rain starts because you've had this gust front come through. Bigger clusters are called a mesoscale convective complex. Sometimes they're called mesoscale convective systems. But it's kind of a circular area of thunderstorms with many cells kind of embedded in one big cluster or complex. And these things can put down a phenomenal amount of rain, and they have some of the most vivid lightning you'll ever see. They're most common in the northern plains in the Midwest. We don't get them as much in the Middle Atlantic in the Southeast. So the conditions for getting the formation of thunderstorms: humid air, not a shock if you've lived in the Southeast, the Mid-Atlantic, any length of time. In the lower to middle part of the troposphere, 0 to 3,000, 4,000 feet. Atmospheric instability, meaning it's a lot colder aloft than it is closer to the ground. I mean, it's colder aloft, but a lot colder aloft. And then something to push that air upward, a source of uplift. Sometimes just the heat of the day itself can force warm currents of air to start to bubble up, like bubbles at the bottom of a pan on a stove. But sometimes we've got cold air coming in from a cold front, a big continental polar air mass racing out of the Canadian prairies, smashing into a hot, humid air mass here in Virginia, Pennsylvania, Alabama, and that forces that air up to form thunderstorms. So those are a couple of classic ways where that happens. A thunderstorm day, it's just any day where you hear thunder. Why we bring that up is to show you where thunderstorms are most common in the United States and North America. Not a surprise. Mostly you see them in Florida. All right. But there are secondary maxima in the Rockies. because, we talk about Denver being the Mile House City. If you've never been to the Front Range of the Rockies, Denver is still reasonably flat, but as soon as you go west, it goes up in a big hurry. So knowing that the elevation goes from about 5,000 feet to 14,000 feet in a very big hurry means that you've got much warmer air immediately to your west. You have warmer air already higher up in the atmosphere by 7,000 or 8,000 feet than you do right here. So that gives your air a little bit of a lift, if you will. You have hot air here, relatively cool air here. So this air is rising and you get natural thunderstorm development at the peaks of mountains. We see that to a secondary effect in the mountains of Southwest Virginia and North Carolina, because those mountains are relatively high as well. That's some of the first places thunderstorms will form, are mountaintops, over top of mountains anyway. Florida, it's a little bit different because it's a peninsula. Okay, so when we think about the summertime in Florida, and we know that the land gets hotter than the ocean. So if your land there in Florida gets hotter than the ocean, and that air starts to rise because the air of the ocean is relatively cooler, this air is hotter, so it starts to rise. So air from the Gulf and the Atlantic starts to push in to take its place. You've got air converging, smashing to itself, forcing more air up to get more thunderstorm development. So you've got sea breezes coming from the Gulf, coming from the Atlantic, smashing into each other, forcing air up and getting thunderstorms. And of course, if you've ever been to Florida in July, you know it's insanely hot and humid. So there's lots of energy to make thunderstorms. But because there's no real cold air nearby, it's hard to get truly severe thunderstorms. These kinds of thunderstorms that are going to put down large hail or put down 60, 65 mile an hour winds. It can happen, but it doesn't happen much in Florida. Florida is mostly just about the very heavy rain because there's so much moisture available there in the summer. California, we don't get them as much. Why? Because it's right next to the relatively cool Pacific Ocean. Gulf of Mexico and the Atlantic, these things are running 80, 82, 84 degrees as we get into the summer. All right. The peninsula itself is running 90, 91. All right. But, even if you get to 75, 80, 85 in Southern California, the ocean's still 68 to 70. It's a lot cooler because the cool ocean current coming in from the north. So thunderstorm development is a lot harder in California. It just doesn't happen as much. A severe thunderstorm, again, this is a term that gets tossed around a lot, but when you hear weather folk like me talking about a severe thunderstorm, it's something very specific. That means the winds have gone above 50 knots, 55 miles per hour, 56 miles per hour. That's strong enough where you really start having damage to trees and structures. You can start to peel off pieces of a roof. Roof doesn't fly off, but you can start to have a couple shingles get knocked off here or there. Or hailstones about an inch in diameter, about a quarter size or larger. And technically a flash flood or a tornado is present. Can be present in a severe thunderstorm. But most of the time when you hear severe thunderstorm, you're thinking about hail or damaging winds. Okay. Most of the time, these break out in the plains through the middle Atlantic and the southeast. All right. We just do not get them much westward from the Front Range of the Rockies. The strongest severe thunderstorms are the ones that grow into supercells. They kind of save all their energy and then blow up. By that I mean, you want colder air higher up, so you get warm, humid air racing up to form thunderstorms. Fine, but in the plains, which are right next to the plateau, the relatively warm and dry air of Mexico, New Mexico, Arizona, it's not just warm and dry, but there's a plateau that's a few thousand feet higher up into the atmosphere. As some of that warm, dry air comes off the plateau and over top of the plains, it forms kind of a cap. It's a stable layer, right? It's relatively narrow, warm area of air aloft. So when the ground heats up and you start to have these little chunks or parcels of warm, humid air go up, instead of fly up into the sky, they run into the stable air and just kind of die or stall, right? So what happens is during the course of a day, you get the ground heating up and slowly eating away at that stable layer, that temperature inversion, all right, until it finally breaks. That stable layer breaks, that inversion breaks, and there is a massive release of energy in the form of thunderstorms. And if the wind direction is just right, in other words, the winds are from the south, close to the ground level, from the west, 8, 10, 12,000 feet up. As that air rises, it turns. As it rises, the updraft into the thunderstorm starts to spin, and that's what can ultimately lead to the formation of the supercell thunderstorm. The whole thing will start to rotate, and in time can drop a tornado on you. So lightning, of course, is what makes a thunderstorm a thunderstorm. That is an electrical discharge because water is a polarized molecule. It has a plus side and a minus side. And you start developing ice crystals along with water, liquid water, along with water vapor molecules all bumping and crashing into each other. You start to separate electrical charges in the cloud. And then once the potential difference in charges builds up enough, there is a release to equilibrate the electrical charges in the cloud, right? Air is actually a very, very good insulator. It's really hard for electricity to go jumping through the air. It's a very good insulator, all right? But if the charges get close enough, you can overcome that insulation, all right? And the electricity will flow. Think about it. During the dead of winter, when it's dry, there's not as many water molecules running around in the air. It's the whole thing. You rub your feet on the rug, you start developing an electrical charge, and you touch something metal, and you get the little static electricity. I mean, that's electricity coming out of you, jumping into the doorknob, if it's metal, right? It doesn't happen in the summer much because it's more humid in the summer. There's more water vapor in the air bouncing off you all the time, slowly taking that charge away from you in tiny, tiny little bits that you never notice, right? When the air is very dry and there's not a lot of water vapor running around, there's nothing there to start taking charge away from you, then you touch anything metal and the spark jumps, right? So again, air is a very good insulator of electricity normally, right? But you've built up so much electrical potential difference in these clouds that it builds up enough where no amount of air is going to keep electricity from flowing. It overcomes it. Thunder is a shock wave, effectively because lightning is hotter than the surface of the sun. And when lightning strikes, it superheats the air instantaneously to literally to 50,000 degrees. All right. And then almost just as rapidly as it happened, it's gone. So you have a humongous and very, very short-lived change in pressure and temperature, up and back. And that generates a shock wave, which is what we hear as thunder. And you maybe remember from the grade school days how to tell how far away lightning is from you from the time you see lightning and you count to 5. 1, 2, 3, 4, 5. If you hear thunder, that means that the lightning strike was about a mile away because sound only travels about 750 miles an hour compared to the speed of light, which is 186,000 miles a second, which is effectively instantaneous here. So it takes a while for the sound to get to you, unless, of course, the lightning strike is right here when it's all apparently instantaneous. Within the thunderstorm is, in addition to the gusty winds, some of the winds can be especially strong. These are called the downburst winds. It's a very strong downdraft. We talked a little bit about the rain-cooled air that comes out of the thunderstorm runs out ahead of the storm. Sometimes in very slow-moving thunderstorms, or ironically very fast-moving thunderstorms, that air can come down very rapidly. I mean, literally, you can have the downburst, the rain-cooled air within a thunderstorm rushing down at 100 miles per hour, rushing down, going out in all directions. The analogy to this is go to your kitchen sink and just turn it on full blast. Water comes down, smashes, goes out in all directions. It's the same thing with the downburst. The very narrow ones are called microbursts because they're really, really concentrated in a small area. All right. But these are the things that can cause airplanes to get messed up. Because if you're trying to fly your airplane and the wind is coming this way, and you get on the other side of the downburst, and all of a sudden the wind's coming this way, it drives your plane into the ground because you don't have lift anymore. So downbursts is what oftentimes causes straight line wind damage in the middle Atlantic, the Northeast, and even the Southeast. A lot of times people I know it was a tornado. No, it wasn't. No, it wasn't. It was probably a downburst. You can easily have downburst winds that are 100 miles an hour. At the end of the day, it's moving air, it's wind that causes damage. Sometimes it makes people feel better about themselves because they think it was a tornado, because they don't believe it was a downburst because they don't know any better. Sorry, just don't know any better. All right, but most of the time it's a downburst. The derecho was made famous in Virginia in 2012. It is a family of straight line wind, downburst winds, that's massive. All right, this thing, it's like a squall line, but it's hundreds of miles long, and the winds are exceptionally strong, 80, 90, 100 miles an hour for a very long time. Very long time, I mean like half an hour, a long time. There's a very bad derecho that went through Iowa last summer, caused all kinds of damage in Cedar Rapids. Google Cedar Rapids derecho 2020, and you'll know more than you want to know about what happened there. But it's a very long-lived, long line of downburst winds. For the slower moving storms, we get very heavy rain that can turn into flash floods. A flash flood is a flood that happens in a flash, thus the term, but it also retreats as rapidly as it comes. And this normally means within the course of a few hours. It rises in a few hours and it's gone in a few hours. Compared to like a big river flood, which lasts for a couple of days to a few weeks, these things happen in streams, creeks, smaller flowing bodies of water. It just rains like crazy in the watershed area, and the water comes up, it floods, and then a few hours later, it's all back within its banks. It tends to happen more in the late afternoon and into the nighttime because that's when most of your thunderstorms happen. All right. The biggest places that need to worry about this are like mountain valleys, because water's going to collect in a valley, or urban areas that don't drain particularly well. You've got all this pavement, it can overwhelm storm drains. So urban areas, mountain valleys, these are places that are especially susceptible to flash floods. Finally, hail. Some people get hail confused with sleet. They're both balls of ice. Sleet is happening in the wintertime, and that's just snow that melts and then refreezes on the way back down. Hail forms differently because the cloud overall is warmer. you get some melting of your precipitation. It begins to fall, but then gets caught in some of the thunderstorm updrafts, and it kind of cycles back up above the freezing level in the cloud, so it freezes again. Bumps into other supercooled water, begins to fall because it's a little heavier. And then it can get caught into another updraft. Depending on how strong the updraft is, will determine how big your hailstone can grow. If you've got very massive updrafts, your hail can grow bigger than the size of a quarter, up to a $50. Tennis balls, there's occasionally softball size hail. All right. So you have to have a very intense updraft to get hail, very large hail. But hail tends to go in cycles within a cloud until finally it becomes heavy enough to fall out. And that's why in the biggest hailstones, you can actually slice them open and they look like onions because they're in layers because of that, going up and down through the melting level of the thunderstorm. So tornadoes, of course, have always been a big point of popular culture all the way back to the Wizard of Oz days. But a tornado, by definition, is a violent rotating column of air in contact with the ground. Normally with a supercell thunderstorm, but not always. The biggest ones tend to be associated with supercell thunderstorms. The tornado itself is not necessarily visible. What we think of as looking at a tornado is a condensation funnel because they normally form in humid environments. And when you have a big circulating vortex, it gets cool. So there's condensation around it. And that's what we see as the funnel, the condensation funnel. But sometimes it's just as easy to see all the debris that's being spun around it. So it doesn't necessarily have to have a condensation funnel, but it does have to be in contact with the ground. Sometimes there's a spinning. You can start to see the spinning coming down out of the base of the cloud, but it hasn't gotten all the way to the ground yet. In that case, we just call it a funnel cloud. That particular picture is from Palm Sunday outbreak back in the 1960s in Indiana, with two, I believe, F3 tornadoes almost next to each other. Very infamous tornado outbreak. So the condensation funnel is tiny water droplets, as most clouds are. The weaker tornadoes aren't on the ground very long and can only be a few minutes. Some of these are these little EF0s, EF1s. They don't last very long at all. To the other end of the spectrum, you've got tornadoes that are a mile across and can be on the ground for 30, 40 minutes at a time. So they come in a myriad of shapes and sizes. You can have a tornado that lasts 2 or 3 minutes, and they're hard to detect because they're very small. They last 2 or 3 minutes, and they're gone. All right, but those are normally the smaller tornadoes, and I say only in quotation marks, that have 60 or 70 mile an hour winds. You might flip over a small car or take off a piece of a roof, but they're not going to obliterate your house. But the biggest threat from tornadoes is from stuff flying around. That's why we tell people to, when there's a tornado warning, go the heck inside, get low to the ground and away from windows. Because what you're trying to do is avoid being hit by something flying through the air. When you've got winds blowing at 80, 100, 120 miles per hour, little things that you don't think are going to do damage can do damage when they're moving that fast. Trees, power poles, sticks, cinder blocks start flying around, they're going to hurt or kill you. Okay? That's why you want to get below ground if you can. But if you can't, at least get into the most interior part of whatever structure you're in and low to the ground as possible. All right? Most people are not picked up by a tornado and taken somewhere. That doesn't really happen much. I mean, it can happen, but it's probably not going to happen. The last thing you need to worry about is being sucked up by a tornado and being taken to Fredericksburg. That's not going to happen. All right. Flying debris is where it's at. The F scale goes from 0 to 5. Ted Fujita originated this scale back in the early 1970s. Then in the late 90s, early 2000s, it was kind of revisited by a lot of professionals in the severe weather sciences, if you will, and kind of recalibrated, but still the same 0 to 5 scale is maintained. Light damage to incredible damage. Incredible meaning it's just nothing left. There's just nothing left. There's just sticks, twigs, chunks of houses, cinder blocks crushed, cars wrapped around trees, all kinds of just insane stuff. All right, those EF5s are not something you ever want a part of. Tornado Alley, and it's interesting this term comes up right now because this is a term that is becoming to fall out of vogue. The classic tornado alley is that north-south area in the high plains, Kansas, Oklahoma, Nebraska, North Texas, even up into South Dakota, which is where the most prevalent large tornadoes can be found. But as we have seen, as detection methods have gotten better, and we can find tornadoes with radar better than we used to 40 or 50 years ago when the term tornado alley was invented. Actually 60, 70 years ago now. We know that there are a lot of small and medium grade tornadoes in the Mid-South, Alabama, Mississippi, Georgia, Tennessee. So the whole idea of a tornado alley is becoming less and less acceptable. What you see there is the number of tornadoes per year. All right. The number you see there is in red in Mississippi and Alabama. The thing about those tornadoes in the Mid-South, a lot of them happen very late in the afternoon or at night. And unlike the ones on the plains, the plains there aren't a lot of trees around, as there are in Mississippi, Alabama, Georgia, Tennessee, the Carolinas. The tornadoes that hit these places can be more wrapped in rainfall. They're coming through more forested areas. They're harder to prepare for quickly than in Oklahoma and Kansas, where these wide open plains and you can see the thing from a mile away. You can't necessarily do that in the central time zone or, in Kentucky, Tennessee, Mississippi, Alabama. It's too forested. So the incidence of, unfortunately, fatalities is higher in those locations because of that and the fact that they are more common at night. Don't get lulled into this idea that terrain or mountains will protect you from tornadoes, because they don't. They don't. Especially the strong to violent tornadoes don't care at all. I mean, that just doesn't matter. A little more than half of the tornadoes form during the warmest hours of the day and into the evening. So, 3, 4 o'clock in the afternoon on through about 7, 8 o'clock in the evening, late spring and summer. All right, the peak months are from May to June, and the worst of the tornado season tends to migrate northward as spring turns into summer. In other words, in the spring, the early spring, tornadoes are more likely in the south. By the time we get to June, they're more likely farther north toward Minnesota, Wisconsin, Michigan in June, whereas March and April are much more common farther south in the Mid-South, Texas, those locations. All right. The reason for that is that as we get into the spring and very early summer, the upper part of the atmosphere, 10, 15, 20,000 feet up, is still relatively cool from the winter. Remember, the ground is heated. The sun heats the ground heats the air, right? So it's that area close to the ground that's going to be a lot warmer than the air 10 to 15,000 feet up. That air that's 10 to 15,000 feet up takes a lot longer to warm than the air close to the ground through the course of weeks and months going into the summer. So if you have very warm ground and much colder air above it, you have more instability and you're more likely to have thunderstorms and ultimately tornadoes. Finally, we get into tropical cyclones, which is the larger characteristic or nomenclature of tropical storms and hurricanes. A tropical cyclone is a warm core system compared to winter storms, mid-Atlantic cyclones, or baroclinic cyclones that are cold core systems. In the middle, they're cold. Tropical cyclones are warm, and they almost always form over warm ocean waters. This is why we don't get them in February, all right, at least in the northern hemisphere. Tropical storms and hurricanes are both tropical cyclones, or just different levels of tropical cyclone. So tropical cyclone, warm core system. That's what you need to know. If it's tropical, it has a warm core, not a cold core, a warm core. It's getting all of its energy from latent heat release. Remember, you evaporate and then you get the condensation. There's a big heat release. Well, if you got a big honking warm ocean and you start to evaporate that and it goes up into the atmosphere, and you've got so much of that moisture condensing out, releasing heat energy into the atmosphere, that's your warm core system. All right, that's why it needs to happen over warm ocean water. That's why you don't get it happening over Minnesota in January. There's no warm ocean water in January in Minnesota. Okay, so 4 categories. Tropical disturbance, that's not even quite a cyclone yet. That's just like, oh, look, there's a little cluster of showers and thunder showers in the tropics. That's nice. It's not that much to it. But when they start to organize a little bit and spin just a hint, it's called a tropical depression. There's a small relative area of low pressure around this cluster of showers and thunderstorms, and the winds around it get up above about 23, 24 miles per hour. All right. What happens is you'll have a couple of thunderstorms forming. They rise. That leaves a small area of low pressure in between them. If the ambient wind is not strong around them, because it's normally not in the tropics, so you have big temperature gradients, you have a small area of low pressure, more air kind of moves around it to take its place, which can lead to more vertical motion upward and more thunderstorm development. Technically, it's called convective instability of the second kind, if you see that somewhere. All right, but it's warm core. All right, tropical depression is when we see that happen enough where you've got the wind speeds at least 23 miles per hour. Tropical storm, the wind speeds, the maximum sustained wind speeds, not just the gusts, but someplace where the winds are sustained, the 2-minute average wind speeds, at least 39 miles per hour. That's when the storm will take a name. A, B, C, D, E, F, G, whatever. All right. Once the maximum sustained winds reach 74 miles per hour, then it's a full-on hurricane. All right, but the maximum sustained winds have to be 74 miles per hour for it to be a hurricane. Doesn't mean everywhere in the hurricane it's 74 miles per hour. Normally it's not. Okay, the maximum sustained winds are oftentimes in one quadrant of the storm until you get into very mature storms, these class 3, 4, and 5 storms with that very, very well-defined eyes. And I'll talk about what the eye is in a minute. I think you probably know what that is. But again, these happen in late summer, early fall, because that's how long it takes the oceans to get warmed up. Remember, it takes a lot of energy to warm up the ocean. That's why the ocean's not warm in May, at least in our part of the world. It takes a while. By the time we get into June, July, and especially August and early September, ocean's gotten quite warm because summer. The sun's been beating on that ocean for a couple months, for a long time, and it's finally raised the temperature of the ocean. So this is why we see these storms most common in August and September in our part of the world. And into early October, then the water starts to cool off a little bit. But you need to be over warm ocean water to get the energy to fuel these things. The eye, of course, is the center of the storm where there's very little cloud cover. There's not a lot of wind. All right, that's where the air is actually sinking in the thunderstorm. All right, the worst of the weather is right around the eye and the eye wall. That's the ring of thunderstorm clouds, cumulonimbus clouds to be technical. They have the heaviest rains and the strongest winds. All right. The hurricane is not always symmetrical. All right. But the worst is almost always in the eye wall. To get to the eye, you got to go through the eye wall. All right, and that's where the worst of the air, that's where the worst of the weather is. That's where the winds are the strongest. So when we talk about the winds, the maximum sustained winds are 140 miles per hour. Well, where is that? That's in the eye wall. Over, 70, 80 miles away from the eye, you're probably not going to have those 140 mile an hour winds. They're probably 80, 90 miles an hour. But that's not where your strongest winds are going to be. Your strongest winds are going to be around that eye wall. And I remember talking to elementary school kids who were like, well, how come you just can't spend the whole time in the eye? Because it's not bad there. It's like, well, you got to go through the eye wall first. And that's the really unpleasant part. The hazards, of course, some of these are obvious. The damaging winds, and of course, heavy rain, inland flooding. They can also make tornadoes. As these things come on shore, there is a change in wind velocity or wind shear. In other words, when the wind is over the water, there's less friction, right? So when the hurricane comes on shore, that wind starts to suddenly drag a little bit on the ground. Just there's a decrease in the wind speed, not much, but a decrease. So there's a little change in wind speed with height, and that could initiate a little bit of wind shear or a little spin, which can cause tornadoes with landfall and hurricanes. In addition to the very heavy rain causing flooding on streams and creeks, 30, 50, 70 miles inland, of course, there's the storm surge. At the coastline, as the storm comes on shore, the wind is pushing water onto the land. If you think about the flow around, the spin around a hurricane in the clockwise fashion, and if you think about a coastline, if you think about the Gulf Coast, so you've got land to the north, the Gulf of Mexico to the south, and the storm is traveling from south to north, the wind around that is clockwise. So on the right side of the storm, or in this case, the east side of the storm, the wind is from the south and it is pushing water up on the shore. And that's the storm surge. And depending on how big the storm is, how strong the winds are, what the coastline shape is, concave, convex, how the water is going to pile up, goes a long way in determining how bad your storm surge is going to be. Whether it's a few feet or 10 feet or worse. Some places 15 feet and the worst. Once the storm does finally get on land all the way, I mean, not just the eye itself, but the entire circulation gets on land, it will begin to diminish. Obviously, it's not instantaneous. Depending how strong it was in the first place, will go a long way in determining how fast the hurricane begins to weaken. But even once it is inland, you can still get the tornadoes. You will still get very heavy rain. And you'll still get at least at minimum some gusty winds, for a couple of days, for sure. Depending how fast the system moves, you can still very easily get flooding 2, 3, 4 days once the storm moves inland. If you think about Hurricane Harvey in Texas back in 2017, it was no longer really a hurricane when it was putting down some of its heaviest rain. Right? One of the things that people forget is that as visual as damaging winds can be, when we talk about hurricanes, as much structural damage those winds will do, the visuals of stuff flying around through the air in 110, 120 mile an hour winds, the flooding does more damage. The flooding does more long-term damage because it covers a lot more area. Right? Flooding does more damage, especially if the storm is moving slowly. All right. So yes, the wind gets a lot of press, but me and a lot of other folks who talk about weather for a living try to remind people the flooding can cause more damage, and it can sneak up on you if you're not paying attention. Again, part of this is because of the Saffir-Simpson scale. It's an engineering scale to determine how much structural damage from the wind the storm will do. And this is more of a wind and pressure metric. It does incorporate storm surge, but that's an idealized storm surge for an idealized coastline. So don't get locked into, a Category 2 storm is only going to have this amount of storm surge. No, when we talk about a category storm, we're really talking about the winds. The storm surge is more idealized. When we're really trying to define, quantify what category a storm is, 1, 2, 3, 4, 5, we are looking at the winds. The winds normally correlate to a central pressure, but when you get that information from the National Hurricane Center, what scale is it? Nowadays, that is all about the maximum sustained wind speed. Not the gust, the maximum sustained wind speed. As I mentioned before, you got to have warm ocean water. All right. Generally, about 80 degrees Fahrenheit. And we've seen it at 76, 77 degrees, but it's also got to be relatively deep, 100, 150 feet worth of that kind of temperature. Otherwise, you start upwelling some of that colder water, 68, 70 degree water. That's 100 meters down. If that begins to get pushed up for all the wave action going on in the storm, that's going to cut back on how intense the storm is. Adequate Coriolis effect. By that I mean, although these things start in the tropics, you don't see them at the equator. Remember, the Coriolis force depends on being on a rotating sphere. And if you're at 0 degrees latitude, there's not much spin going on there. You need to get 8 or 9 degrees of latitude away from the equator to start developing enough spin on your planet to translate into a spinning area of low pressure. Or else you're not going to get the spin you need to develop a hurricane. A hurricane is an area of low pressure that is spinning. So if you don't have any spin, right at the equator, you're not going to get a hurricane. All right, so you need to be at least 8 or 9 degrees of latitude away from the equator. And then likewise, not a lot of strong winds aloft. During the winter and spring and fall, we have a lot stronger winds aloft, jet stream level. We've got winds 10, 15,000 feet up. The winds are regularly 40, 50 miles an hour. That's not the case in the middle of summer. We don't have as much temperature gradient. There's not as much change in temperature during the summer as we have in the winter over a lateral distance. So when you don't have as much change in temperature over a lateral distance, whether it be north, south, or east, west, you don't have as much wind. And that means the same thing higher up in the sky as well. Right? To get the hurricane to form, you need a concentration of the energy. Another reason we don't have them forming in the dead of winter is because there's too much wind aloft. It would just kind of rip the hurricane apart. So you don't want any strong ambient winds in the tropics to start tearing apart your hurricane. It forms a lot differently than mid-latitude baroclinic cyclones, rainstorms, snowstorms, coastal storms. They're different. They form fundamentally differently. Yes, they're both spinning things that make a lot of precip, but the origins of it, the way it develops, the energy it gets to develop, form in different ways. Warm core versus cold core. Again, most of these, you get 8 to 20 degree latitude belts as a general rule. Sometimes you see them form a little bit farther north or south. On average, you get about 80 of these every year. And those are the basins, if you will, the places where they form. the Atlantic, the Eastern Pacific, the Western Pacific North and South, and Indian Ocean. These are where the water is typically the warmest during the local summers. Remember, the warmest water on the whole dang planet is there in the Western Pacific, so that's where you get a maximum of tropical cyclones. There, Japan, Philippines, into China, Korea, those locations. And over there, they're called typhoons, but they're exactly the same physical being. They have different names because of just the local lexicon. Different parts of the world have given these things different names hundreds of years ago, and the names have just stuck. All right. But hurricane, typhoon, tropical cyclone, they're all exactly the same thing. It's a warm core system with an eye. It gets all of its energy from warm ocean water. In fact, in Australia, they just call them cyclones. But they're all the same dang thing. On average, you get about 2 hurricanes striking the coast each year. 2005 set a new record until last year, set a new record in 2020 when we had 30 of these things and went into the Greek alphabet for names. Oh, and by the way, just a couple of weeks ago, the World Meteorological Organization, which the United States is a part of and has some pull, decided to not have Greek letters for hurricanes anymore. So if we run out of names like we did in 2005, 2020, we're not going to go to the Greek alphabet. We've set aside another special series of names in case that was ever going to happen again. All right, so we have 6 master lists of names that rotate every 6 years to name hurricanes in the Atlantic. All right, so this is 2021. We'll use the same list of names in 2027. We'll use the same list of names in 2035. All right. If you get a really bad storm that does a lot of damage, that name will be retired. Another name will take its place. But the same basic series of 6 names, list of 6 names, persists. All right. But there hasn't been a big trend in the number of tropical cyclones in the Atlantic. Despite the planet warming, it's not the number that we are fearing that's going to go up, but the intensity of the ones that do form is going to get worse. That's a big thing about hurricanes and climate change. It isn't the number of them. Yes, we had a lot last year, but there are a lot of other things going on. We talked about El Nino, La Nina. There are a couple other things going on. Pressure changes, pressure patterns, ocean patterns, contributing to the number of tropical cyclones / hurricanes. As we think about a warming climate, it isn't the number, it's the intensity of them. They produce more rain, they can produce stronger winds, they might reach a higher category. You might have more category 4s than 3s than you did in the past. Right? So what isn't the number is the intensity that we think about going forward in a warming climate. In spite of the high frequency in the Eastern Pacific, it's very hard for storms in the Eastern Pacific to get into North America because most of the time they form and then move out. They're moving from east to west back out into the open Pacific. So even though they might form, near the Mexican coast, the Pacific Mexican coast, they will then move out into the open waters of the Pacific. On rare occasions, jet stream winds will buckle. They'll turn one of these things back into California or into the coast of Mexico, but that's the exception rather than the rule. Finally, when we look at the hurricane life cycle, because the steering winds are so light, remember, we don't want a lot of wind to get these things to form. So steering winds are very, very light. These things have very odd trajectories, right? But as a general rule, they kind of move along from east to west with the trade winds. Then at some point they begin to hook more to the north and then back out to sea once they get caught up in the main jet stream flow, or the westerlies as we call them. All right, so they kind of chug along in the tropic. They start to nudge north, and then they turn back off to the northeast. That's the general pattern. All right, but as you can see, they're not always that way. There are several exceptions, but the general idea is they move across the Atlantic from east to west, then turn to the north, and then back off to the northeast. And that's it. So that's a lot. Next time, we will talk about natural climate change, how we know climate has changed in the past without us ever being here. Things like the Milankovitch cycles. We'll talk more about that, solar cycles, all that kind of stuff. So we'll get into that next time. So thanks. This is a long one. Appreciate everybody. Go back and watch it a couple of times. The lecture notes will also be posted as well. A lot of good information there about temperature and severe weather.